We'll get started. So, if you recall, we are starting our foray into gradient descent algorithms. Take a deep breath. Now, the actual optimization class is going to start. Um, and until the end of the semester, we are only going to be talking about algorithms. Okay. So, we'll talk about necessary and sufficient conditions for optimality, and then we'll jump into algorithms. Okay. So, that's the format of the rest of the lecture in this semester. Uh, okay, so what did we talk in the previous lecture? I want to minimize a function f of x lies in Rn. And in the previous lecture, we were talking about this fact that I want to pick a direction d in which to descend, and I want to make sure that the value of the function is going to be the value of the function should decrease after I take a step in that direction. So I'm standing at a current point x naught, and I identify a descent direction, and I take a step here, and then my function value is lower at this point, and now I have to figure out the descent direction again. So maybe now the descent direction is going to change, and I'm going to take a step in that direction, and now the function value is lower, and so on and so forth. So this process is supposed to go on. One of the things we recognized in the previous lecture was we should pick d to be equal to minus gradient of fx, and instead of taking a very long step in that direction, because this O of d term, we don't want this O of d term to dominate this particular term, so I want this term to be smaller than this term. So somebody mentioned that we need to pick an alpha, which is the step size. And so the class of algorithms that we came up with is my xk plus 1 equals to xk plus alpha k dk. So at every point of time, at every iteration k, I'm going to pick a descent direction dk, I'm going to pick a step size alpha k, and then I'm going to get to a point xk plus 1. And the desirable property of xk plus 1 is I want to make sure that the function value at xk plus 1 is smaller than the function value at xk. So we want f of xk plus 1 to be strictly less than f of xk. So although in the previous class we said that I want d to be negative of gradient, I'm going to be slightly more general now, and I'm going to say that I want my dk to be minus dk gradient of fxk, and this capital dk is a positive definite matrix. Okay, so dk is strictly positive. It's a positive definite matrix. Let's see if this changes the narrative. Uh, why would a positive definite matrix help? So let's think about it. So here dk is equal to I. So it's an identity matrix. Definitely identity matrix is a positive definite matrix. So this one kind of fit the bill of this algorithm. But let's think about why dk is important. Why should we have a positive definite matrix? So let's first see whether having a positive definite matrix here makes any sense. Does it satisfy this condition? Okay, so I have f of xk minus alpha k dk gradient of fxk. Remember, alpha k is small, so this is f of xk minus alpha k One thing I forgot to note, I want alpha k to be strictly positive. Okay. Any questions so far? This is the Taylor series expansion, something that we have now become very comfortable with, something that will be our bread and butter for the rest of the semester.
For the higher order terms, why we are only putting alpha k?
Because you can technically write alpha k and norm of decay, but because alpha k is the thing that we will control most, I'm just writing alpha k here. Alpha k, I can make it as small as possible. Decay, I really cannot do much. So once I pick my positive definite matrix and the gradient, there's nothing much that I can scale there, but alpha k is something that's within my control. Any other question? Okay, so what do we notice here? I have a non-zero vector transpose a positive definite matrix multiplied by a non-zero vector. This term is strictly positive. I have negative alpha k, so this term is strictly negative. I have something that goes to 0 as alpha k goes to 0. So by picking alpha k sufficiently small, I can make this term very small. So what I have is, by picking an appropriate value of alpha k that is close to 0 but not 0, it still has to be positive. But let's say I'll pick alpha k to be 0.1 or 0.01 or something like that. So I will make this term very close to 0. And this term is going to be strictly negative. So that means that this whole thing is going to be less than f of xk. So actually this fits the bill. So if I make this algorithm like this, it does satisfy fxk plus 1 is less than f of xk. So in the sense I'm descending, I'm taking a good step in the right direction where the function value is reducing. But the question still remains. So yes, I can make this decay, I can pick a positive definite matrix, but why should I pick a positive definite matrix? How does that help? Okay, so one thing that you should always remember, in optimization, more is always better. The more things you can control, the better it is for you. I mean, okay, so maybe not the I don't want to say it's better for you, but if you make a judicious choice of more parameters, you can make the convergence faster. Okay, and faster convergence is what we are going after. So far, we said, this algorithm is going to go in the right direction. I'm going to reduce the function value. But remember, our goal in optimization is to get to X star as soon as possible. If method one gets to X star in 1 million time steps, 1 million iterations, 1 million of these iterations, I want to get to X star in 1,000 iterations. How can I get that order of magnitude reduction? So having this positive definite matrix will allow you to get order of magnitude reduction in the number of steps you need to take to get to the optimal solution. What is the drawback with this problem? So I added this decay term here, I added this positive definite matrix, and potentially I could go from 1 million time steps to 1,000 time steps. But why would I not go get something done in 1,000 time steps? Why do I want to take 1 million time steps? 1 million steps, million Ks to get to X star.
What's the drawback of it?
What's the drawback of this method?
You have more to tune.
Right. So you definitely have more things to tune. So how does that affect the real world performance of an algorithm?
So we would need to do more processing.
You have to do more processing. So per step processing is going to increase with this method. Okay. So here is another way to think about it. So I want to get to the solution as soon as possible. If I have to take 1 million step and each step takes 1 millisecond, then that's 1,000 second stuff. If I have to take 1,000 steps, but each step takes 100 seconds to execute. Now you're looking at a algorithm that's going to take 100,000 time steps, 100,000 seconds to execute. So one thing that you always have to trade off as an optimization person is the computational complexity and the time complexity. So how much time does it take, and how much computational, like how many iterations do you need to run? And there is no good way to measure both of them. So ultimately, the performance depends on how you have actually written the code and executed on the machine. So ultimately it boils down to how you are setting up the problem. But something that we also need to keep in mind, no matter which industry, which field you go to, um, you have to keep both these things in mind. The thing that we will not talk about is memory complexity. So let's say I'm talking about this chat GPT, right? So DK now is 1.8 trillion cross 1.8 trillion matrix. How are you going to store that matrix? 1.8 trillion cross 1.8 trillion dimensional matrix. Where are you going to store it? How are you going to execute that process? So then there are obvious reasons why uh, you may run into memory complexity as well. But we are not going to talk about memory complexity. We are not going to talk about time complexity. The only thing I'm going to comment about is how many iterations k would be roughly needed to solve that problem. Okay, wonderful. So now the question becomes, wonderful, we have two things to choose. One is alpha k, one is dk. So what are the different ways by which we can pick alpha k and dk? So let's get into that. So how do we pick dk? Steepest descent. This is dk equals to identity matrix. This is the stuff that we talked about in the previous class. This is steepest descent algorithm. Newton's method. Dk equals to second derivative of the function evaluated at xk inverse. So okay, I want to pause here for a bit. So I have steepest descent. I picked the dumbest dk I can potentially think of, which is just an identity matrix. Then I have Newton's method, and we have come up with a very complicated decay. So I have to take the second derivative of the function. So I have to spend some amount of my time computing the second derivative. Okay. So if the function is e raised to x, computing the second derivative is easy, it's e raised to x. If the function is very complicated, you might have to resort to numerical differentiation in order to compute the second derivative. Now you compute a matrix, n cross n matrix, and now you have to invert that matrix. Okay. So this decay takes a lot of effort to compute. Now if it's a 3 cross 3 matrix, it's probably not that difficult. If it's a million cross million matrix, it's very difficult. Okay. So one sort of tidbit of information. So we were working on a vehicle optimization problem. It had 3 states. So xk was sort of 3-dimensional, and so computing the second derivative inverse was not a big challenge. But we were computing the second derivative inverse on a microcontroller. Okay. So on MATLAB, we don't think about computing a second derivative inverse, but on a microcontroller, you have to think about it. Okay. You don't have as many registers, you don't have as much RAM, so you have to think about whether computation of second derivative inverse is a big deal or not. So just because it's a 3 cross 3 matrix doesn't mean it's easy to invert a matrix, let alone compute the derivative of a function. Now it turns out that Newton's method is much order of magnitude better than steepest descent, for the reason that we'll cover maybe in this class or the next class. So Newton's method is very good, amazing, at an expense of higher computational cost per iteration. Steepest descent is okay, it does well, at the expense of very low computational cost per iteration. So Newton's method converges very fast, this one converges slowly. So I want to get the benefit of Newton's method without necessarily the per step computation cost of Newton's method. And this is a very important point. So I see like there is a shiny method there, and I want to try and emulate that shiny method, but I can't really spend that much amount of computational effort onto that shiny method. So people come up with what is known as diagonally scaled steepest descent. So I don't want to compute the second derivative, the cross second derivative terms. I just want to compute the second derivative with respect to xi, evaluate it at xk. By the way, this xi is the ith component of x, and this xk is the vector xk. So don't get confused. Unfortunately, I don't have a better way to represent this on Blackboard. So this is xi, the second derivative of the ith component. You evaluate it at xk, you invert it. This is your diagonally scaled steepest descent. So it kind of retains some property of Newton's method. You have some small computational cost here, but it will perform better than the steepest descent method. What else can you do? Yes.
Are we assuming f is convex?
We are not assuming f is convex. Very good question. So for the rest of the discussion, f is not convex. So the second derivative, if it is negative, you can't do the invert there, because then this is not a positive definite matrix. So we'll talk about those situations in a bit. Okay. Any other question? How can you further improve the method? So we talked about 3 methods. What's the pattern that you are seeing? So second derivative inverse seems to be an important thing, and I don't want to spend the computational cost. I want to keep the computational cost at a minimum. So what else can I do? Can you think of some ways to reduce the computational cost per iteration? Let me give you a hint. So remember, I'm taking small steps. So I picked x naught, I took picked a decay, and then I took a small step. So x1 is not too different from x naught. X2 is not too different from x1. X3 is not too different from x2. What does that tell you about Newton's method? So how can we get the benefit of Newton's method? So I can pick dk to be second derivative of f at x naught inverse. Okay, so I compute the second derivative inverse once at the beginning of the iteration, and I just keep using it for the rest of the solution.
You just compute that once and
Then just let it be. Yeah. Then let the entire iteration use this dk. Then there is discretized Newton's method. Dk equals to hk inverse. Hk is an approximation to get second derivative of the function f. So you can compute the second derivative through some sort of approximation, finite difference formula, whatever comes to your mind that can allow you to approximate the second derivative of the function. You could also have a situation where the function f has multiple terms, but some of the terms do not have a second derivative, so you kind of, or the second derivative is very close to zero, so you kind of ignore those terms and just keep the ones that contributes the maximum amount to the second derivative and keep those terms and then invert those terms only. Okay, so we'll see an example of it when we are talking about least square algorithms for solving least square problems. Okay, that's pretty much all the different methods that we talked about. I mean, that people study. There are some variations and stuff that we'll talk about in a bit in subsequent classes, not in today's class. But these are roughly the recipe for creating algorithms for solving unconstrained optimization problems. Okay. There are more recipes, but this is a generic sort of recipe, and we'll study more recipes in the future. Any questions so far? So one thing that I want to go over is what is the difference between steepest descent and Newton's method. Okay, so there is another way to think about steepest descent and Newton's method. So let me go over that. Okay, so I have f of x plus alpha d. Maybe not alpha, I'll just keep f of x plus d. F of x plus gradient of f of x transpose d. Sorry, this is not equal to, this is approximately equal to What do you feel about the second approximation and the first approximation? So I asked someone to do a Taylor series approximation of f of x plus d. Person 1 came up with this approximation, person 2 came up with this approximation. Okay. Now, it's kind of intuitive that this approximation is better than this approximation. Okay, because this is considering higher order terms, and this one is not considering that second order term of the Taylor series expansion. Okay, so So let's change the problem. So I wanted to find a descent direction. I wanted to find d such that f of xk plus 1 is less than f of xk. I'm going to change the problem statement and I'm going to say I want to minimize over all d in Rn f of x plus d. So I'm standing at x, I'm looking for a descent direction, and I want to figure out which direction d I should take a step in. Now, people will say, okay, this problem is difficult. So I'm going to say, okay, well, we have these two approximations, so let's substitute these two approximations. So I get minimum over all d f of x plus gradient of fx transpose d, and I get the other one minimum over all d of f of x plus so this is what I want to solve, but I cannot solve this because this is as difficult as the original problem I started with. This seems doable, and this one seems doable. Okay, so let's figure out what do you think is the solution to this particular problem? So this term doesn't depend on d at all. It's only this term that depends on d. I have a matrix transpose d and I want to minimize this particular value. Okay, so let's think about it. So I have a vector gradient of fx. I want to find a d that has the minimum inner product with respect to the vector. So which vector in this space will have minimum inner product with respect to this vector? The answer to that is the vector that's going exactly in the opposite direction of the original vector. What's the inner product of a vector which is 180-degree apart of that particular vector? Well, it's going to be negative of the norm of the vector. Okay, so the solution here is negative gradient of f of x. Now, of course, somebody who is more mathematically mature would argue that I can pick d star to be negative infinity gradient of fx, and then this term is going to become negative infinity, and that's the best thing. But remember, I'm just looking for a direction. I don't care about the magnitude because ultimately the magnitude is controlled by alpha, not d. Okay, so I'm just looking for a d star. What about this problem? Okay, what's the d star for this particular problem? So this one doesn't depend on d. I have a affine term in d and I have a quadratic term in d. And oh, this one is second derivative. Assume that the second derivative is positive definite. In that case, this is a convex function of d. Okay, so I have a convex function in d. What do we know about solving a convex problem? Well, we studied in the previous class that x star is optimal if and only if gradient f of x star is equal to 0 for convex functions f. So f is convex, right? So we studied this in the previous class. So all I have to do is take the first derivative of this function and set it equal to 0 and I get d star, right? So this is what we studied in the previous class. I'm going to apply it here. So what's the derivative? This is gradient with respect to d of, let me, what's this derivative? So the first term doesn't depend on d. So derivative is 0. The second term is A transpose D. So the derivative is gradient of f of x. The third term has two d's. This is the first d, this is the second d. So I have to take I have to first take the derivative with respect to the first t and then take the derivative with respect to the second d. So I get half of plus half of. Okay, this is what I get. Yes.
Addition before the.
Oh yeah, yeah. Thank you. Thank you. Okay, so this is the derivative with respect to d. So I get this is the second derivative, sorry, first derivative of this particular function. And then I need to set the first derivative at d star to be equal to 0. So let me do that. So gradient of fx plus second derivative d star equals to 0. This means d star equals to second derivative inverse first derivative. So that's the solution to this. And this is my dk, remember? This is my dk right here, second derivative inverse. Okay, so what this tells us is if you have a better approximation of the function and you can find the descent direction d in a easier fashion, like low complexity calculation fashion, then you can design new algorithms for whatever problem you have. So this is actually the recipe that I use in my entire research. So somebody gives me a function, I want to minimize f of x. The creativity of research goes into finding what is the best approximation to the function where I can compute d star very easily. Oh yeah, there should be a negative sign, yeah. Yeah, perfect. Okay, so that's how the algorithms are designed. That's how most, and this is a recurring theme. This is going to be a recurring theme throughout the course. We have to optimize function 1. Function 1 is very difficult to optimize. So I'm going to compute function 2, which will be a function of the descent direction d. And we'll try to figure out what is the d that is easier to compute so that this particular function better approximates this function. And then we keep building iterates that are picking the descent direction dk at xk. Okay, so all of these methods are finding the best descent direction at xk. Okay, at xk. Any questions so far? Yes.
Are there any methods based on like Fourier series to approximate?
That's a good question. So the question is, are there algorithms that uses Fourier series to approximate? So it does happen in image processing, MRI processing, like like those kind of. So if you are doing medical image processing, you don't tend to set up the optimization problem as a function of the image. You take the Fourier transform of the image, and then you try to set up the optimization problem that is doing some optimization of the Fourier coefficients. Or Fourier coefficients goes into the optimization thing. So if you want to detect a tumor in a medical image, what you are looking for is very high Fourier coefficient. So then you kind of sort of it's not my field, so I'm just uh, telling you what I've seen in some candidacy exams and defense and so on. So you take the Fourier coefficients and then you kind of do something with those Fourier coefficients. Or, like we are talking about 5G, like our phones, right? So whenever our phones are communicating with the transmitter, that those are electromagnetic waves propagation. So you don't really optimize the wave, but you optimize the Fourier coefficients of the wave and which direction you want to communicate to. That sort of comes out of not the original signal, but the Fourier coefficients of the signal. Okay, so there are situations where you don't want to work in the original X space, but you want to work in the omega space. Okay, so to say. But I don't work on those problems, so I know nothing about them. Okay. Any other question? So, by the way, there are, so I'm recording these lectures, and so the voice gets recorded. Now, if you want to remove all the noise from the voice, then again you have to do optimization in the Fourier space. Okay. Uh, yeah, so there are softwares that do that. Any musician here in this room? Nobody plays guitar, or you do? Okay, piano, guitar, and things like that. So they also use a lot of complicated amps and so on, which again does optimization in Fourier domain internally, like within those boxes, they are doing some optimization stuff in the Fourier domain. Okay, awesome. So these methods are, so what we have figured out so far is how to compute dk. What we need to figure out is how to compute alpha k. Remember, we have two things to choose from, alpha k and dk. So let's look into how to pick alpha k. So alpha k is known as step size. So you have minimization rule. Minimization rule. So alpha k equals to argmin alpha greater than 0 f of xk plus alpha dk. Argmin alpha Okay, so everyone has noted it down. So there are many ways to pick alpha k. There's one more way, Armijo's rule, that I'll talk about in a bit. The first one is fairly simple and straightforward. I'm sitting at xk. I have identified the direction dk by picking an appropriate dk from here and multiplying it by the gradient, negative of the gradient of fxk. So I've picked dk, I have picked xk. Now I need to pick alpha. So I'm going to look at the direction dk. I'm standing at xk, I'm looking at the direction dk, and I'll pick the alpha that minimizes the function in that particular direction, whatever alpha I get in that direction. Okay, so that's the minimization rule. Now somebody will come and say, look, this particular optimization problem is very difficult because I'm looking at potentially alpha equals to 1 million, 1 billion, 1 trillion as well. Okay, I don't want to look that far. Then somebody else will come and say, okay, let's use limited minimization. So I'm only going to look at until alpha bar. Okay, so, and then I'll pick alpha k according to whatever minimizes, whatever alpha minimizes this particular function. Then somebody will say, look, these two are pretty pathetic. You have to solve a minimization problem while I'm solving an outer minimization problem. I don't want to use this complicated stuff. I'm training an LLM. I have like 1.8 trillion parameters. I can't be doing this argmin stuff business. It's not my business. Then you can use constant step size. So I'll pick an alpha, alpha equals to 0.1, and I'll just keep using that alpha forever. Then people from large language models will say, look, this one doesn't work. So initially this alpha k equals to alpha works very well. So I get to some point in the space, and after that I'm just walking around that space. I'm not really converging to the solution. So then people will say, okay, well, then you need to keep reducing the value of alpha as the iteration progresses. Okay, so then the question becomes, okay, how do we reduce the value of alpha as the iteration progresses if I cannot use a constant step size? And I don't want to do all this argument business. That's too complicated for me. Then there comes diminishing step size, where you pick alpha k that sums to infinity. But if you pick alpha k square and you sum it up, it actually is a finite number. Okay, so summation of alpha k diverges, but summation of square of alpha k converges. Okay, it doesn't diverge. So this is known as a diminishing step size. The reason for picking this alpha k square less than infinity is fairly complicated, so we are not going to talk about it. But if you take a class in reinforcement learning or machine learning or stochastic processes or probability theory, which is a 7,000 level math class or 6,000 level math class, you will know why this particular condition is being imposed on this alpha k. But it's not something that I can talk about in this class. Okay, so typical examples of sequences of this type is 1 over k, 1 over k log k, 1 over k raised to 2, 2 over 3, and so on. But it cannot be, alpha k cannot be 1 over k raised to 1.01. Okay, the reason is this particular sequence actually is less than, it's summable, it's less than infinity. Okay, so summation of alpha k doesn't diverge. So this, we don't want that. Everything else is a fair game. Okay. Okay, you can also pick C1 over C2 plus K. Okay, so depending on your interest and your problem statement, you can pick one diminishing step size, and hopefully that should work for your problem. Okay, so let's go to the last step size selection rule called Armijo's rule. So Armijo's rule tries to do something that is limited minimization without solving this argmin problem. So argmin is very complicated. So what Armijo's rule is trying to say is, look, I'm going to pick a few step sizes, and I'm going to look at how much the function value reduces by. If it reduces by a lot, then I'm going to pick that step size. If it doesn't reduce by a lot, I'm going to reduce the step size and try again. Okay, so it's an iterative algorithm for computing step size. So your step size alpha k is equal to s beta raised to mk, where s is a positive number, beta is less than 1. And mk is the smallest integer. Well, I'm saying integer, but what I really mean is greater than equal to 0, such that fxk minus f of xk plus s beta raised to m dk is greater than equal to minus sigma beta raised to m transpose dk.
Sigma constant.
Sigma is some other constant. So you pick sigma, let's say sigma equals to 0.1 or 0.6 or something. It's another positive constant. Okay, so you start with m equals to 0, check whether this condition is satisfied or not. If it is not satisfied, then you pick m equals to 1, check if this condition is satisfied or not. If it doesn't satisfy, then pick m equals to 2 if this condition is satisfied. Okay, it's satisfied for m equals to 2, perfect. S beta raised to 2 becomes your alpha k. If it satisfies for m equals to 0, alpha k equals to s. Okay. So Armio's rule is trying to do something like this, 0 to s. This is what it's trying to solve. But instead of solving this argument problem, which is a very complicated minimization problem, Armio's rule is saying, look, if s works, great. If not, then I'll pick s beta, check if this condition is satisfied. If it doesn't work, then I'll pick s beta square, check if this condition is satisfied or not. If it is satisfied, that's it. S beta square is my step size. So that's the benefit of Armio's rule. Now, what is a drawback of Armio's rule? So I'm not solving this problem, right? It's definitely more complicated than constant step size, certainly more complicated than diminishing step size. Okay, but there is furthermore, I mean, it has some other drawbacks as well. And I want you to think about what other drawbacks this might have. Armio's rule. In other words, why would training of large language models not use Armio's rule? This seems like a very good model to use. Yeah.
It's more processing, basically.
So where are you doing processing in this?
Computing the function, for example.
Computing the function. So function evaluation. Whenever function evaluation is a problem, derivative you have to compute anyway. So this is something you've already computed. This is something you've already computed. That's just natural process. Inner product is not that big of a deal. It's still a deal, but not big of a deal. Okay, so this part is easy to compute. This is a part which takes complicated effort if your function f is very complicated. Okay, so when I'm training large language models or when I'm doing some complicated machine learning training, or for that matter, if you're using a small microprocessor and your function is say log of x or e raised to x or something like that, right? So it's not a polynomial, but it's actually a some sort of infinite series on a small microcontroller. Now, how do you compute function, right? So now you have to do a lot of iterations in order to compute the function. And what Armio's rule is saying is you need to keep checking this again and again. So in one step, you might have 30 or 40 different function evaluation. Okay, so that's why Armio's rule becomes difficult when function evaluation is difficult. Okay, and function evaluation being difficult is a function of both the problem statement and the hardware on which you are doing the function evaluation. Okay. Any question? No.
Why we have
Yeah.
why we have the constraint?
Which this constraint?
Mm-hmm.
So, when you are taking a step, you want to make sure that the function is decreasing by a certain magnitude. Okay, then how do you decide what is the magnitude by which the function is going to decrease? So if you think about it, this is just a first order Taylor series expansion, right? So the sigma term is what is controlling how much you want the function to reduce by. And sometimes if the function landscape looks something like this, right, and you pick the step size, which is, and you're standing here, this is your xk, this is your dk, and this is your xk plus sdk, you see that the function is not reducing by a big amount. This is all the function is reducing by. So f of xk plus sdk, which is this number, is basically just this much. So you want to make sure that the function, the improvement at xk plus s beta dk, the improvement in the reduction is significant enough for you to be able to take that step size. So that's why you have to have the sigma term, and you're trying to look for that signal when you're doing function evaluation. Okay. Wonderful. Yeah, you have a question? No? Okay. Okay, wonderful. So I think we are done with this particular lecture. We'll meet again in the next lecture, and we are going to be talking about least square problem. Oh, also the convergence results for these algorithms, and then least square problem is what we'll talk about. Thank you. See you on Friday.